and she has just joined us here. As I said, she has received funding from various different organisations, the Leeuwenhoek Trust, the Royal Society, Banff International, Research Station, Portuguese Association for Research Students, and now SFI, the Irish Research Council and SFI, with a Pathways Award, which is a 4-year fellowship here at the Institute. And she's going to tell us tonight about some of her work on cosmological issues with old and new mysteries of dark matter. And it's a great pleasure to introduce. Yes.
Thank you very much, Denjo, for that nice introduction. And I'm very happy to be here today to give this talk to you as part of this wonderful festival, especially since I'm particularly fond of this time of the year. So as mentioned, I'm going to tell you a bit about some old mysteries of dark energy and some new mysteries of dark energy. There's a lot of dark energy in the universe. Specifically, today, 70% of the energy in the universe is composed of dark energy. And I'll get more into this in my talk, but the very existence of dark energy is a big puzzle to us. And it's a very active area of research today to try and understand the origin and nature of dark energy. Now, compounding on what we already didn't know about dark energy, over the past decade or so, there have emerged some new mysteries, which we technically call cosmological tensions, about dark energy. So because of these new mysteries of dark energy, it's actually a particularly exciting time today to be thinking about dark energy. So as a theoretical physicist, there's nothing more enticing than some puzzle that the universe throws at us, which we just can't ignore. And if we're stuck for a long time trying to solve that puzzle, which we have been with the old mysteries of dark energy, then having a couple of new puzzles, new additional puzzles, but related puzzles to also think about, can provide the fresh perspective that we need to hopefully understand all of these things together. And this is the situation we find ourselves in regarding dark energy, and I'm going to tell you about this today. So dark energy is a property of the whole universe. And the study of the whole universe is called cosmology. So before I introduce dark energy, I just want to say a few general things about cosmology. And I first just want to take a moment to appreciate just how ambitious the goal of cosmology is. So as I mentioned, cosmology is the study of the entire universe and the laws that govern it. This is informed by both theory and observation, and it includes understanding its origin, its present properties and nature, its future and evolution, and its ultimate fate. So the universe is the biggest system that we try to study in physics, bigger than anything else. Now, we know that the universe wasn't always so big, but for much of its history, it's been very, very big, and much bigger than anything else that we study. Even in astrophysics, when we study faraway objects and big objects like stars and planets, we're still talking about scales that are much, much smaller than we're talking about in cosmology, let alone when we think about particle physics and nuclear physics. And usually we think that the physics that's relevant at one scale is independent of the physics that's relevant at another very different scale. But we think there are hints that cosmology might be an exception to this, that the physics of different scales might be relevant to ultimately understanding cosmology. And I'll come back to this point a bit later in the talk. Another thing I just want to mention is that there are some philosophical similarities between studying cosmology and trying to understand things like consciousness or artificial intelligence. So we are part of our own brains, and we have limited access to our brains. And similarly, we are part of the universe, and we have limited access to the universe. So we have to make a lot of indirect inferences about the universe. And we're not guaranteed to necessarily be able to figure out everything about how it all works, but we're trying to see how far we can get. And at least so far, there has been ongoing progress in understanding the properties of our universe. So here are some general facts about our universe. On large scales and on average, the universe looks more or less the same everywhere, or we say that it's homogeneous. And again, on average and on large scales, the universe looks more or less the same in every direction, which we say it is isotropic. And notice that I said on average and on large scales, because obviously on small scales there are some differences. We see stars and galaxies in some places, but not in others. And we also think that we don't occupy a special place in the universe. So for example, we don't think any longer that we're at the center of the universe. So we assume that the universe is homogeneous and isotropic, no matter where we view it from. This is known as the cosmological principle. It also means that there is no edge to the universe. So another fact about the universe is that the visible universe contains billions of galaxies. The majority of matter in the universe is something called dark matter. So it's a kind of matter that neither emits nor absorbs visible light. And similar to dark energy, it's something that we know very little about. We know that the universe started with a Big Bang, which is a very early period where the universe was very hot and very dense. And since the Big Bang, it has aged to be around 13.8 billion years old, and its contents have since the Big Bang diluted and cooled down a lot. Another important fact about the universe is that it is expanding. So Edwin Hubble, pictured here, was the first to notice this back in 1929. So Hubble noticed that there was a certain relation between the recessional velocities of faraway galaxies and their distance to us. So the relation that he found was that the velocities of those galaxies was proportional to their distance away from us. And the proportionality constant we call Hubble's constant, and it is usually expressed by the symbol h0. So the velocities of distant galaxies are equal to h0 times the distances of those galaxies. And this relation is also called Hubble's law. Here is sort of a more modern version of the original data that Hubble worked with. So on the vertical axis is the velocities, and on the horizontal axis is the distance. And they're both in units to make the numbers more or less nice and small. So the circles are the values of the data points. The vertical and horizontal lines are the estimated errors from the observed values of the data points. And the solid line over here is the best linear fit through this data, and the two dashed lines are the best linear fits one standard deviation away from the main fit. So if you sort of eyeball it, Hubble's constant, which would be the slope of this line, is roughly 2,000 divided by 30 in these units. So it's somewhere between 60 and 70 in these units. Apparently, Hubble was also very athletic. For example, he played basketball, baseball, track and field, among other things. So once we know that the universe is expanding, the next natural question to ask is that expansion slowing down or is it speeding up? So up to the late 1990s, most physicists expected the expansion of the universe to slow down over time. And let me explain why they expected the expansion to slow down. So up until the 1990s, physicists thought that the universe only consisted of matter and radiation. Now, if we also assume homogeneity and isotropy, so the universe looking the same everywhere and in every direction, which remember is the cosmological principle, then the dynamics and evolution of our universe is governed by a differential equation called the Friedmann equation. So this is Alexander Friedmann who came up with this equation using Einstein's theory of general relativity. So this is the Friedmann equation. A is something known as the scale factor, and it basically tracks the size of the universe. So the bigger A is, the bigger the universe is. The smaller A is, the smaller the universe is. This omega ret and omega mat are constants related to the energy density of radiation and matter, respectively. And the dot on this A corresponds to a time derivative. So we have this equation, and we can, if we assume that the universe is radiation dominated, which basically means that this radiation term is much bigger than this matter term, we can go ahead and solve this differential equation. And the solution that we get is that the scale factor A over time is proportional to square root of time, and A dot, or the time derivative of A, is proportional to 1 over square root of t. So even though over time A is growing, the derivative, or the rate of change of A over time, is decreasing. And we can do the same thing in a universe that is this time matter dominated. So now this term is much bigger than this term. Again, we can go ahead and solve this equation, and we get that the scale factor A over time is proportional to time to the power 2/3, and A dot, or the time derivative of A, is proportional to 1 over the cube root of time. So in both cases, the scale factor A is growing with time, but its derivative is decreasing with time. And in case we don't have a matter or radiation-dominated universe, and we have some mixture of these, we would qualitatively just get a behavior in between these two, but the qualitative behavior in both cases is the same. So then in all cases, whether it's radiation-dominated, matter-dominated, or a mix of the two, the general behavior is that the scale factor is increasing with time, but its time derivative is decreasing with time. So this is why researchers expected the expansion to slow down over time. But in 1998, to the surprise of everyone, it was discovered that the expansion is actually speeding up. So A dot is actually growing with time, and this discovery was made by 2 independent teams led by Saul Perlmutter, Brian Schmidt, and Adam Rees, and they won the 2011 Nobel Prize for this discovery. So they made this discovery that the expansion is growing over time using the redshifted light from distant supernovae. So supernovae are very bright exploding stars whose properties, like their frequencies, we understand pretty well. And the redshifting of light means that when you look at the frequencies, or the spectrum of frequencies of these supernovas, or whatever light we're looking at, the redshifting of it means that those frequencies are shifted from shorter wavelengths to longer wavelengths. And dark energy is the name that we give to whatever extra thing is needed to account for this speeding up of the expansion of the universe. We don't know what it is. We just know that there needs to be some extra thing to cause the universe's expansion to speed up over time. Now we have some ideas for how to model this dark energy. And one of the simplest and most successful models for this dark energy is called the cosmological constant. So the cosmological constant is usually expressed with the Greek symbol, Greek letter capital Lambda. And actually, before we even knew about the expansion of the universe and the accelerated expansion of the universe, Einstein introduced such a cosmological constant term in a model of the universe that he had. But he introduced it for a very different reason than we use it nowadays. So he introduced such a cosmological constant because he needed it in order to make the universe static in a model of the universe that he had. So he just really liked the idea of a static universe that wasn't changing over time. Although he had to abandon his model because obviously it was discovered that our universe isn't static, it's expanding. And so it's a little bit ironic that we are using the same cosmological constant now to describe the accelerating expansion of the universe, unlike why Einstein introduced it to describe its staticness. So if we go back to our Friedmann equation, the cosmological constant is just a constant term added to these matter and radiation terms. And we can repeat our exercise of solving this equation, this time in a universe that is dominated by dark energy, or this lambda term. So this lambda term being much, much bigger than these two other terms. And the solution we find is that the scale factor A, as well as its time derivative, are now growing functions with time, and specifically exponentially growing functions with time. So it's in this way that introducing a cosmological constant gives us a model that causes the expansion of the universe to be speeding up over time. And this whole right-hand side in this Friedmann equation is actually the total energy density of the universe. And the different components are the contributions from the different kinds of matter or energy that we now know the universe is made up of. So this part is the radiation energy density. This part is the matter energy density. And this part is the dark energy density. And each of these terms dilutes over time very differently. So over here is a plot of each of these energy densities versus time. The radiation one is the one that dilutes the most quickly. It's this one. So it quickly over time drops down to very, very low values. The next fastest to dilute is the matter energy density. So it drops down slower than radiation, but it too drops down fairly quickly. And then finally, the energy density doesn't dilute at all, at least for this cosmological constant picture. It just stays constant. It starts out with a value that's much, much smaller than both the radiation and energy density. But over time, as the radiation and matter energies dilute, it eventually takes them over. And this is what we mean when we say that, for example, 70% of the energy density of the universe is dark energy. We mean that we've reached a time where the matter and radiation densities have gone so far below the dark energy density that it's dark energy that's dominating on the right-hand side here, and specifically making up for 70% of the amount on the right-hand side. And over time, these matter and energy densities are going to keep going down, and the cosmological constant is going to keep staying constant. So the this fraction or this percentage is only going to grow over time. So it's going to be 80%, 90%, and so on of the energy budget of the universe. Now, we know that we stuck in this cosmological constant term because it mimics the effect of dark energy very well, but theoretically motivating it, and especially with a value that would be consistent with a lot of observational data that we have, is a notoriously difficult task. It actually turns out that quantum theory also predicts that in nature there should be such a cosmological constant term, a sort of energy that's associated to empty space, which we call vacuum energy. But according to quantum theory, the natural value that the cosmological constant would take in some units is 1, or it's infinity if we're not careful and we don't bound the energies. And in contrast, the value that we need for the cosmological constant in order to explain a lot of observations that we have in those same units where quantum theory predicts 1 is actually 10 to the minus 120. So the value that quantum theory tells us that lambda should naturally take is 120 orders of magnitude bigger than the value that we need to explain observations. And this is sometimes said to be the worst prediction in the history of theoretical physics. So if the explanation for lambda is indeed this vacuum energy from quantum theory, we have a lot of explaining to do. And the explaining that we need to do is usually summarized as 2 cosmological constant puzzles. One of them being explaining why, we can summarize these two puzzles as being explaining why is the cosmological constant or its value 0, and secondly, why is the value of the cosmological constant not 0? So what we mean by this is, first we need to explain why is the value of the cosmological constant so much smaller than the value that it naturally wants to take according to quantum theory. And secondly, we need to explain, well, why is it not just 0? Because if it had been 0, then we can imagine that maybe we could explain it by some sort of cancellation using a similar term that gave this value of 1 in the first place. But getting a cancellation that would give such an unnatural and small residue is a lot more difficult to achieve. It's a lot more contrived. So that's why we need to explain both why it's so much smaller than 1 and why does it take this strangely non-zero finite value. Right. So setting aside this issue of theoretically motivating the value of the cosmological constant, this model of the cosmological constant has actually done remarkably well to explain a whole range of data that we have of the universe. This data ranges from data that we have from the very early universe, for example, the cosmic microwave background radiation, which is radiation from very shortly after the Big Bang, as well as some more late time data that we have from objects such as supernovae. So it does a really good job at explaining a whole bunch of different cosmological data that we have from different eras and different objects. So everything that I've told you so far would fall into the category of old mysteries in dark energy. So let me just summarize them. So in 1998, everyone was surprised by supernova observations revealing that the expansion of the universe is speeding up, and we named the cause of this dark energy, which we don't know what it is. We just know that it's some extra thing needed to cause the speeding up of the expansion. So we know that dark energy has a gravitationally repulsive behavior that pushes galaxies away from us. There are some candidate models for dark energy, such as the cosmological constant model that I told you about. And these fit observations very well, but we have a difficult time theoretically motivating them. And of course, if the origin of the cosmological constant is this vacuum energy of quantum theory, then we also need to explain the cosmological constant puzzles. So even though a minute ago I just told you that the cosmological constant model fits observational data very well, what has been happening over recent years is that our observational data has just been getting better and better over time, more and more precise. And the cosmological constant hasn't quite been keeping up with it. So there are some cracks starting to show, and we call these cracks or these slight mismatches between observations and what we expect from the cosmological constant model, cosmological tensions. So one of these cosmological tensions is called the Hubble tension. And the issue is that there are different values for Hubble's constant h0, which was this proportionality constant between the velocities and distances of distant galaxies, that we predict from some of the early universe data that we have, namely the cosmic microwave background radiation, and some of the late universe observational data that we have, for example, from the supernova data. And depending on which particular data sets we consider, the disagreement is a little bit better or worse, but more or less we say that the discrepancy is at the 5 sigma level, which is a statistical term that intuitively it means that the chances that the cosmological constant model explains this data is about 1 in 3.5 million. So it's pretty bad. And here's a sort of timeline of this Hubble tension. So it's, I guess, not showing up super well, but okay. So the blue data points and their estimated errors, which are the vertical lines, are different data sets over the years that have been published from local objects or more late time observational data that we have, such as the supernova. And the black points and the estimated errors are data that we have had, again, over the years from early universe cosmic microwave background radiation data. And so what has been happening is that in the earlier years, the data from these sort of two independent regimes of the universe has had large errors associated with it, and a good area of overlap between the two different data sets. But what has happened over time is that our measurements have become more and more precise, so these estimated errors have shrunken in size over the years, and there's sort of been a branching off or a forking of the values preferred by these two different data sets. So this is where we're at, close to today. And so these vertical lines, they account for every kind of error that we could think of possibly going on in our measurements of these values. And once we account for these errors, we're finding that we're getting different values for this Hubble constant if we look at early universe data or if we look at the supernova data. And this shouldn't be the case. So if we're accounting for all our errors, we shouldn't be getting distinct values for the same thing. But this is what we're getting, and this is what the Hubble tension is about. It's about understanding why are we getting these these two distinct non-overlapping values or ranges of values for the Hubble constant. Another important tension that has recently risen is called the S8 tension. So S8 is a parameter that measures the amount of inhomogeneity or clumpiness at the intergalactic scales in our universe. So similarly, there's a discrepancy between the values of this amount of inhomogeneities or structure that we get if we look at early universe cosmic microwave background radiation data, or if we look at later universe data such as from the supernova. Again, depending on which particular data sets we consider, the discrepancy is a little bit better or worse, but on average it's around the 3 to 4 sigma level, which translates to the fact that the chances that the cosmological constant model describes this data is less than 3 in 1,000. So again, it's pretty bad. And here's one representation of this tension. So this red line is the value for this S8 parameter that we get if we look at the early universe cosmic microwave background radiation data. And the blue line and corresponding data points and errors are from various different independent late universe observations. Now there are a few that overlap this red line, but for the most part, most of these observations, and which happen to be most of the ones that observational cosmologists trust, tend to disagree with this red line. So we have this other tension, and there are a few other tensions as well, which I'm not going to mention. So these two tensions, the Hubble tension and the S8 tension, are the worst tensions that we have. They're also the two tensions that we think have something to do with dark energy. Now, researchers have thought a lot about what errors they could have made in collecting the data and processing the data to give rise to these tensions, and they really haven't been able to find anything. So the attention has very much turned to theory and how we can rethink the standard model of cosmology, which includes this cosmological constant that is everyone's favorite model of dark energy, and how we can theoretically tackle this problem and revise the cosmological constant model to account for these tensions and remove these tensions. So here's a picture of me and my two PhD supervisors, Nyayesh Afshordi and Raphael Sorkin. So this picture was taken on July 17, 2017, right after my PhD thesis defense. And here's a celebration cake in front of us. So I'm showing you this picture for some context on my background as a researcher. So Nyayesh primarily does research in cosmology, and Raphael primarily does research in something called quantum gravity, which I'll explain in a minute. And despite being mentored by both a cosmologist and a quantum gravity researcher, it wasn't until very recently that I got involved in research that involves both cosmology and quantum gravity at the same time. And the subject that drew me to this was precisely dark energy, and especially these recent tensions and recent mysteries that were emerging regarding dark energy. Now, we don't know if quantum gravity is going to be the key to solving these new mysteries, but it certainly has a big shot at providing a very well-motivated explanation for these mysteries. So for the rest of the talk, I want to tell you a little bit about quantum gravity, and I want to tell you about my favorite potential solution to both the old and new mysteries of dark energy. So first of all, what is quantum gravity in the first place? So quantum gravity is a theory we don't have yet, but once we have it, it will tell us how gravity or space-time, which is the thing that describes space and time, behave at the very highest of energies or the very shortest of distance scale. For example, energies and distances that are relevant at the time of the Big Bang or inside of a black hole. At such high energies and short distances, both quantum theory and gravity are important, hence the need for quantum gravity. We don't yet have a theory of quantum gravity, as I just said, but there are many different proposed frameworks or proposed approaches to trying to formulate a good theory of quantum gravity. And each of these different approaches makes certain assumptions about what is fundamental and what principles are important in nature. So in the cosmological context, we already know that quantum gravity is going to be important for understanding the very early universe, so the Big Bang and shortly after it. But there are hints that it will also be needed to solve the cosmological constant puzzles. And these new tensions, as I mentioned, they're a great opportunity for quantum gravity to play a major role and connect fundamental physics with what we see in the universe at the largest of scales. It's not guaranteed to solve these tensions, but it would be really great if it did, because we would learn both about quantum gravity and about cosmology. So the particular approach to quantum gravity that my research focuses on is called causal set theory. The main premise of causal set theory is that space-time, so the thing that describes space and time, is fundamentally discrete. And the causal relations among those discrete elements is fundamental. So 2 elements or 2 points in space and time are causally related if you can get from one point to the other by traveling at or less than the speed of light. And here's an example of a causal set. So the circles are the discrete elements of space-time, or the discrete elements of the causal set. The lines are the causal relations among the different elements. And the arrow is just the direction of the relation. So for example, we can get from element y to element z by traveling at or less than the speed of light. But for example, we can't get from one of these elements to one of these, we can't get between these 2 elements by traveling at or less than the speed of light. And the main idea is that similar to a fluid like water, which on large scales or macroscopically looks continuous to us, but as we zoom in to very small scales, we start to see the discrete molecular structure of those fluids, that space-time could similarly behave the same way. On large scales, it looks continuous to us, but if we look at it at the very smallest of scales, we start to see the discrete elemental structure that it has. So if you like, we have atoms of space-time underlying what seems like continuous space and time on large scales. And I'm going to tell you about a particular model of dark energy that is a consequence of some key properties of causal sets. So first, let me tell you about some of the key properties of causal sets. So in order for these discrete causal sets to be good representations of space-times that on large scales are continuous, the points need to be distributed in a particular statistical way. The particular statistical way that they need to be distributed in boils down to, if you were to take any arbitrary volume in the macroscopic continuous space-time, that the number of elements on average that would represent that volume would be equal to that volume, with a standard deviation of square root of that volume. By analogy, imagine that you have some cake with icing all over the surface, and you're handed a bunch of sprinkles to decorate the surface of that cake with, and you're tasked with the job of placing those sprinkles such that anyone who gets even a strange shaped or arbitrarily small shaped cake slice would still end up with a good number of sprinkles, or a number of sprinkles proportional to the size of the cake that they're getting. So you want to place those sprinkles in a sort of random but uniform way so that someone wouldn't be able to carve out, snake around the different sprinkles and end up with a slice with no sprinkles on it. So the way these discrete elements need to occupy the space-time is analogous to this most strategic way you would place the sprinkles on the cake so that everyone gets a slice with a good amount of sprinkles on it. Or analogously, every piece of space-time volume ends up with a good number of discrete elements representing it. So here's an example of a causal set that represents a certain type of expanding universe. Another important fact is that dynamically we think of causal sets as growing in number or growing in size over time. So it's almost as if the causal set has some internal clock, and as the clock is ticking, more elements are being born to its future and it's growing in size. So for example, we have this 4-element causal set here, and at a later time, as the clock ticks, we end up with one of these 5-element causal sets. So the passage of time is correlated with the growing in size of the causal set and the number of elements. So if we just put these two facts together, that there is this statistical correspondence between the way the elements need to be situated to represent the continuous space-time well, and the fact that causal sets grow in number over time, then quantum theory tells us that there should be a relation between the value of the cosmological constant lambda and the standard deviation of the distribution of elements n that represents a space-time volume V. And remember from the previous slide that the standard deviation of the distribution of elements was square root of the volume that it is supposed to represent. So the value of the cosmological constant is roughly equal to 1 over the square root of the volume that one is considering. Now, if we want to relate this to our universe, the relevant volume to have in mind is the volume of the universe. And if we plug that into here, we get a number that is 10 to the minus 120, which is exactly the number that we need the cosmological constant to have in order to agree with observations well. So remember, I told you it's very difficult to theoretically motivate this value, but here we have a potential explanation for how this small number arises as connected to the discreteness of space-time in this model rooted in causal set theory. And in this way, we would be solving the old mystery of dark energy. So we would be giving meaning to what this cosmological constant is, and we'd also be motivating the particular value that it takes. This is also an example of what we call UV-IR mixing. So UV stands for ultraviolet or short wavelengths or short distances. And IR stands for infrared or long-range effects or long distances, long wavelengths. And we have UV-IR mixing because we've related something like dark energy, which is a property of our universe as a whole, to the discreteness of space-time at the smallest of scales. So there's interplay between this very large scale effect and this very small scale effect. And it is explanations for dark energy like this that make us believe that in cosmology, different scales will be important, and the physics of different scales will be important. In this case, both quantum theory and quantum gravity, and gravity on larger scales from Einstein's gravity. So this model for the cosmological constant, it's called ever-present lambda, and it was first introduced in 1987. So this is almost a decade before the supernova observations that told us about the accelerating expansion of the universe, and that if described by a cosmological constant, it needs to take this value. So this is not very well known, but in some sense, one could say this was a successful prediction of quantum gravity. And here's just a cartoon picture of how things look like in this model. So these triangles, which are really cones in our four-dimensional universe, represent the observable universe at different times. And the points in them represent the causal set elements that describe the universe at different times. So as the universe evolves, this cosmological constant lambda is actually no longer a constant. It evolves with the volume. So over time, it's actually becoming smaller and smaller because the volume of the universe is getting bigger and bigger, and it is inversely related to the volume. So at early times, it would be having some larger value, and at later times, it would be having some smaller value. And this relation is also up to a sign, so it can have both a positive and a negative value. So I told you about how ever-present lambda does with the old mysteries of dark energy, but what about the new mysteries of dark energy? So it's a little bit early to make any definitive statements, and it's something we are actively currently looking into. So regarding but there are hints that this ever-present lambda model has some of the features that we think will be key to solving the new cosmological tensions and new mysteries. So for example, with the Hubble tension, a lot of models that researchers believe will be key to solving this discrepancy between the early and late values of the Hubble constant are dynamical dark energy models. So what this means is that we don't think of the cosmological constant or dark energy as constant over time, but we think of them as having changed over time. And in particular, models that exhibit early dark energy, so more change at early times, are believed to be important candidates for alleviating or even removing these tensions. So this ever-present lambda model is inherently a dynamical dark energy model because it evolves with the volume of the universe. And it also naturally has a statistically larger value at early times as compared to late times. So it already has some of the features that we think are necessary for solving this Hubble tension mismatch. Here are two of my collaborators, Santanu Das and Arad Nasiri, who I've recently been doing a lot of work on this model with. And for example, one of the things that we've been doing together with Santanu and Arad is to make sure that this ever-present lambda model does well at explaining a lot of the observational data that we have, for example, the supernova data that we have. And we have confirmed that this ever-present lambda model fits supernova data fairly well. Now regarding the S8 tension, again, it's a bit early to make any definitive remarks, but some models that researchers think have the necessary ingredients to solve this tension or alleviate it are very similar to ever-present lambda, or have features that are very similar to ever-present lambda. And those features are that if we have a dark energy model where the value of the cosmological constant or the energy density is changing sign over time or is oscillating, this has been shown to do well at alleviating this tension. And again, these are features that are already present in the ever-present lambda model. It is naturally expected to change sign, and it also has a variation over time. So it has this oscillatory feature. Another class of models that have been proven to be promising in addressing this tension are interacting dark energy models, which basically accommodate a flow of energy from dark matter to dark energy. Now, this is not something that naturally happens in the ever-present lambda model, but it's certainly something that we can incorporate into the ever-present lambda. So all of these ideas that cosmologists have for different ways to alleviate the S8 tension are either already present in the ever-present lambda model or can easily be incorporated into it. And I should also emphasize that when cosmologists have these ideas, these are mostly at the ad hoc level of, just cooking up a model that have these properties. So if they naturally arise in an already well-motivated model, it is preferable. And again, here are two of my collaborators that I've been doing some recent work on ever-present lambda with, Haydar Moradi and Miguel Ziliao. We've been studying a lot of the statistical properties of ever-present lambda. So that would include at what time scales would the sign be changing or the variation be happening at. And so, in summary, we have these old mysteries of dark energy, and we have these new mysteries of dark energy. And some researchers like myself are optimistic that the key to solving these mysteries will be quantum gravity, which is itself a mystery. And this would be nice because it would connect our understanding of fundamental physics with what we observe in the universe at the largest of scales. So, thank you.